first talk in the afternoon session. I mean, I know that Professor Balasubramanian needs no introduction to anyone in mathematics, but I don't want to leave this opportunity to say a few words about him. So Professor R. Balasubramanian, firstly, let me point out he's a pillar of support for Kerala School of Mathematics, and he's a leading light in the theory of numbers, theory of zeta functions, analytic number theory, and leading mathematicians for so many years representing India. So let me say a few of the awards. No, I cannot list all of them, but at least a few of them. That he is a Padma awardee. He is Vatnagar awardee. He has got Lifetime Achievement Award from Government of India. He has got special award from French government for furthering the understanding, the research in mathematics between India and French. He is a fellow of American Mathematical Society, and of course, he is a fellow of all the societies, science societies that we have in India. And of course, he's not many people may know that he is also considered to be father figure in the crypto research that we have in India. He has done, I mean, what is called Waring's conjecture. He finished the final part of Waring's conjecture, and his results, he has done pioneering work on the moments of zeta functions, which are being used everywhere. Professor R. Balasubramanian.
Thank you. Thank you for the organizers, in particular, the director, Kalyan Chakravarti, for this opportunity to talk in this conference. Yeah, I will be talking about the correlation of arithmetic functions. So first of all, explain what they mean. In many situations in number theory, one come across sums of the form G1n, G2n minus h, where G1 and G2 are some arithmetic functions. And I mean, this, for example, G1 can be divisor function and G2 also. Therefore, you will be having D of n minus h, or sometimes D of n, D3 of n minus h, and so on and so forth. There are also situations where the G1 comes from some GL2 function and G2 comes from GL3 functions, and then you wanted to know the shifted sums. These shifted sums are very important in many contexts, but as I was telling, if you are now looking at Dn or the coefficients of a holomorphic cusp forms and things like that, one has to invoke certain estimates on exponential sums in order to get some good estimates for them. This is probably this was the theme of Rita Prasad Munshi also yesterday, that how to do these exponential sums and how to do it by the circle method. But on the other hand, there are certain special situations where instead of these analytic methods, it is possible to do this problem by using elementary methods. And this comes particularly if the G1, G2 are multiplicative functions, which is probably something which I may not really need, but anyway, for the sake of simplicity, let us assume that this is a multiplicative functions. And G1 and G2, the values at primes are rather close to 1. This is in a sense which has to be defined precisely, which I will do. Some typical examples of such functions, and in fact, we will be mainly talking about these functions, even though we shall be talking about the generalities, but our main interest would be the functions of this type. Phi an by n power a, where phi an is n power a into product p dividing n 1 minus 1 over p power a. Therefore, with a is equal to 1, for example, this becomes the usual Euler function. And in this case, when you evaluate it at primes, then phi a p by p power a actually happens to be 1 minus 1 over p power a. And that is rather very close to 1. And similarly, if you look at sigma an by n power a, where sigma an is the sum of the divisors of n, of course, raised to the 8th power. And then if you try to evaluate it at the prime p, then what you get is 1 plus 1 over p. And in this lecture, we shall discuss a few methods to estimate such sums. I mean, this problem has been Again, by elementary method. I am not even going to talk about any analytic methods at all. But by the elementary methods, this problem have been attacked in 2-3 methods, and I would like to probably say shortly about every method. The one, for example, as I was telling, this is a sum of two functions, g1, g2, but in fact, you can actually take more functions, g1 of a1n plus b1, g2 of a2n plus b2, up to gs of asn plus bs. S functions you can take and take the shifted sums and take the product and then sum over n up to x, 1 over x. In this case, Stepakos obtains a nice asymptotic formula. And we will now explain what the asymptotic formula is, and we shall explain it for the special case s is equal to 2 with the general. Therefore, we will state the result for s equal to 2. Therefore, in particular, we have a sum s of x, which is 1 over x into summation over n, g1 of a1n plus b1 and g2 of a2n plus b2. Again, for simplicity, we assume that a1, a2, b1, b2 are fixed. Even if they, I mean, the original result even allows them to go to infinity slowly, but it's okay. And again, for the simplicity, we will assume that a1 and b1 are co-prime and a2 and b2 are co-prime. And now we want to do this summation, and then we want to see how big is this error term, and then probably we will see what happens in the special cases which we were considering. We fix a parameter r which goes to infinity, and write your g1 as 1 star little g1, and g2 is 1 star little g2, and the delta is a1 b2 minus a2 b1. And now the first thing is what would be the expected main term? The expected main term, once you are assuming that g1 of p is close to 1, then for any such a sum, then you would expect that summation n not exceeding x, g1 of a1n plus b1 into g2 of a2n plus b2 will be constant times x. And the constant has to be the product of the local factors. And that means, okay, therefore we should know what are the local factors. Therefore, this omega p, which is a local factor, this is a summation over m1 and m2, g1 p power m1, g2 p power m2, divided by the LCD of p power m1, p power m2, where the summation is over m1, m2, with the GCD dividing delta, and p power m1 being co-prime to a1 and p power m2 being co-prime to a2. Note that this means for large primes, minimum of m1, m2 will be 0. And now I have to see what, therefore this omega p is of course the local factor. And once you have this omega p as a local factor, you take the product of them, and that gives you p of x is equal to product p dot exceeding x omega p. And now you would like to know what is the main term and what is the error term. And now I was saying that these things we are only saying for g1p and g2p are close to 1. And now recall this g1 and g2 or capital G1 and capital G2 are given in terms of the little g1, g2, namely capital G1 equal to 1 star little g1 and g2 equal to 1 star little g2. This would mean that g1 of p equal to 1 plus g1 of p, little g1 of p, and g2 of p equal to 1 plus little g2 of p. Therefore, the g1 and g2 are close to 1 is equivalent to saying that this little g1 of p and little g2 of p are rather small. Now, I said earlier that when the g1 of p and g2 of p rather small means we have to say precisely in what sense they are small. And the assumptions which we are making is that g1 of p plus g2 of p divided by p, that summation is bounded for r less than or equal to p less than or equal to x. And then we also need some estimate on the capital G, and we will assume that the psi n is a decreasing function of n, which is bounded by a power of log n, such as gjn is less than or equal to psi of n. Under these conditions, the theorem says s of x equal to p of x, as we would expect, will provided a half less than alpha less than 1, and gives an error term and explicit error term. And what we are now interested in knowing is what happens to this explicit error terms in the cases in which we are interested. And that would give you, for example, if you take this function phi n by n, of course, which satisfies the conditions, the corresponding phi p by p is very close to 1, and then take it as phi n plus 1 by n plus 1, and then the expected mean term is rather something which is very easy to write, and then there's an error term, this 1 over log power a, 1 over log x power a, when a for some any a between 0 and 2. Now, this is the sum which you will get. This is one method. This is under the assumption. That's the only point which I want to make again clear. That is, under the assumption that G1P plus G2P by P is essentially convergent. That's the assumption which we are making. Now let me talk about a second method which was done essentially by Murthy, Kopala, and Saha. And this is the following. You recall that the Ramanujan sum, CRN, is defined by the summation e power 2 pi a n by r, where the summation lies between 1 and r, and a and r are co-prime, which also you can also write as summation d dividing n, d dividing r, mu of r by d. And now one says that this f, a function f, admits a Ramanujan expansion if this f of n can be written as a linear combination of this CRN with some complex coefficients f hat. Okay. Now, given this, therefore, suppose you are given functions f and g which admit a Ramanujan expansion, then is it possible to get the summation of the shifted sum? That's the question. And yeah, first of all, let me go back, forget the condition first. Therefore, f of n, g of n plus h, n up to n is equal to capital N, which is the, because as I was telling, more or less in all these cases, the type of cases which we are considering, the summation n not exceeding n, f of n, g of n plus h, we expect only to be constant times capital N, and the constant exactly what is what you are interested in know, and the constant is f hat or g hat or CRH plus an error, and the error is O of n power 1 minus delta log n power 4 minus delta if delta is less than 1, O of log cubed n delta equal to 1, and O of 1 if delta is bigger than 1. And this is now the condition which says is that the Ramanujan coefficients f hat r and g hat r should be smaller than 1 over r power 1 plus delta. Under the conditions that f hat r and g hat r is smaller than r power 1 plus delta, then you have an asymptotic formula. And now, does this asymptotic formula work for the cases in which we are interested? For example, it does work. For example, let me talk about the sigma Sn divided by n power s. If you take sigma Sn by n power s, then it was proved by Ramanujan himself that this function admits a Ramanujan expansion, and the corresponding Ramanujan coefficients are 1 over r power s plus 1 up to a factor zeta s plus 1. Therefore, this is sigma Sn by n power s is equal to summation 1 over r power s plus 1 CNR multiplied by a zeta of s plus 1. And therefore, now you also have a Ramanujan expansion for Fn and Gn, and then you have, we can compute, we know also the f hat r, and then put the value of f hat r, and then depending upon the delta, then you will get this. And that in this particular case, this delta happens to be the minimum of the s and t. If you take f of n equal to sigma Sn divided by n power s, and g of n equal to sigma t of n divided by n power t, then this delta is minimum of s and t, and with this delta, then you have this result. Summation fn by n plus h is equal to summation n, summation f hat or g hat or CRH. But now I want to talk about the third method. In the third method, what I am going to assume is that our real interest is only the functions like phi n by n, sigma n by n, etc. But the functions phi n by n, for example, if you take, then it satisfies actually a condition which is much stronger than G1p plus G2p by divided by p is convergent. Because in this case, G1p is minus 1 over p and G2p is also minus 1 over p, and therefore not only the G1p plus G2p by p is convergent, but G1p plus G2p by any p power alpha is already convergent for every positive alpha. Therefore, you have something which is rather very strong. And therefore, one would like to know whether, assuming such a stronger conditions which are satisfied by phi n by n, is it possible to really look at this problem more closely? And that's exactly what we are going to do. The cases like Gn by Gn, which is phi n by n, where not only Gp, but Gp square, Gp cubed, everything is close to 1. And in this case, a simple convolution method seems to be rather powerful. Okay, therefore, let's do what it is. Consequently, let us assume that f and g are multiplicative, and about this f and g are multiplicative, I will come back a little later. And write again, as usual, capital F equal to 1 plus little of f, 1 star f, and capital G is 1 star g. And now we are looking at those functions where the little fn is O of n power minus alpha. For example, if you are looking, for example, phi n by n as your function capital F, then this little fn, this alpha can be more or less taken to be 1 minus epsilon itself. Under these conditions, we prove n not exceeding x, f of n g of n minus h, obviously n goes bigger than h, is equal to x minus h into c of h plus O of e, where now the e is x power 1 minus alpha, where alpha is less than minimum of 1 and beta, which we can all, I mean, we can assume that alpha is less than beta, and e is x power 1 minus alpha times log x if alpha equal to beta, and log square x if alpha equal to beta equal to 1 and 1 less than alpha less than beta. And what is interesting is that this result is uniform in age, unlike the results which I was talking about earlier. And the CH is precisely summation f of d1 g of d2 divided by the LCM of d1 d2, where d1 d2 bigger than or equal to 1, and d1 the GCD of d1 and d2 divides h. And if h equal to 0, still the same result holds, and then this condition d1 d2 divides h, of course, simply disappears. And therefore, see, that is a CH, which is f of d1 g of d2, and this uniformity is precisely what I want to stress upon. And the same proof actually gives you can get gn plus h also, and the same x into ch plus 1. Oh, sorry, this should be l less than or equal to x rather than 2. And this uniformity is something which I want to stress because of the following reason. Let me go back to that and then come back to the proof. See, earlier with the Sumit Giri, I proved the following result. If f and g are arithmetic function and f equal to 1 star f and g is equal to 1 star g, then f of n g of n minus h is the expected weight term. And now the error term is actually not the L infinity norm of little f and little g, but the L1 norm of little f and little g. And therefore, this error term in many situations seems to be definitely better. And in fact, I don't even need the capital F to be multiplicative or capital G to be multiplicative. I only need the fact that this L1 norm of little f and L1 norm of little g are small, which is essentially equivalent to assuming that a capital F and a capital G has the property that f of p is close to 1 and g of p is close to 1. And okay, first of all, I should say, where did they get this problem from? It was not something which is just out of curiosity we did it. We were actually looking at a problem, the following problem. Suppose you are given an elliptic curve E and you are given an integer n, then I would like to know how many primes P are there. This elliptic curve E is defined over Q. Therefore, I have an elliptic curve E defined over Q and I am taking the minimal model. And this model, I am now reducing modulo P. And I want to know how many primes are there such that this elliptic curve, when I reduce modulo P, the number of elements of this E over Fp will be precisely equal to n. Therefore, if you have an elliptic curve and you look at the number of primes and you want to know how many primes are there such that E over Fp is precisely equal to n, and when you do these calculations, then this summation Fn g of n minus h naturally enters into the picture. And in our case, of course, h was fixed, and therefore we were not so keen on looking at what will be how one would prove the uniform estimate for that purpose. But this is something which I have been looking, and it is not very clear to me how this result can be made uniform in H. And that's why I thought I would make a little more simpler assumptions so that I can make the things uniform in H. And that's exactly the one which I want to prove, give the proof to see where this uniformity comes. Okay. Therefore, I see I have assuming that this f and g are multiplicative, and I am also assuming that this my little f and little g of O of n power minus alpha. Okay. Therefore, let us assume for simplicity E is less than minimum of 1 and beta. And if E alpha is less than minimum of 1 and beta, then by definition, my E of E is equal to x power 1 minus alpha. And that is the error term which I have to obtain. Okay. Therefore, most of the times, when you break the summation, then you break it to mn less than or equal to y type thing. But in order to get the uniformity, you have to break it as the LCM of AB bigger than or equal to x. Look at the second equation. This is the type of equation which I want. Summation LCM of AB bigger than or equal to x, 1 over a power alpha b power beta into LCM of AB is equal to O of EX by x is what I want. And what is the easiest way to prove that? Look at the sum and now split the sum. Split the sum depending upon the value of the GCD of AB. And once you do that, then you end up having a sum like the equation 1. And that sum, summation mn bigger than or equal to y, m power 1 plus alpha, n power 1 plus beta, that summation can be easily done. You should take the summation over n first and the summation over m, and then with the standard argument, it is O of ui by y. And since the summation 2, when you look at it, and when you split the sum depending upon the value of the GCD, it reduces to the summation. It reduces to the equation 1, which you can use and get this result. And this is what we are going to do for various little sums, and then I will explain how these little sums do end up in giving this proof. And similarly, I am not going to explain summation mn not exceeding y 1 over m power alpha n power beta if you take, and from that summation is easy to calculate, and from that we can deduce that when you take the LCM of AB less than or equal to x, 1 over a power alpha b power beta, that will be O of e by x. And this also is obtained essentially by splitting that sum according to the GCD. And now look at the CD less than or equal to y. CD less than or equal to y, c power alpha minus 1, d power beta minus 1. And that summation is again rather easy to do, and that summation will give y power beta, and that would give you CD less than or equal to y, c power alpha d power beta divided by the LCM of c and d is less than or equal to y power beta. But what I will be little later interested is not CD less than or equal to y, but CD bigger than or equal to y. But on the other hand, I would say that the the CD bigger than or equal to y can be actually deduced from what I have on CD less than or equal to y. And that's exactly what I want to say. Therefore, now we claim that when you look at the summation, a power minus alpha, b power minus beta, where the summation is over a dividing m and b dividing m minus k, which is now ab bigger than y. A dividing m, b dividing m minus k, ab bigger than y, the summation over m. This summation is what I want to look at. And this summation is, again, I want to claim that this is order of the E of y, which is y power 1 minus alpha. To see this, write m is equal to AC and m minus k is equal to BD. And then this A you can write as m over C, and the B you can write as m minus k divided by D. And now what happens? That original condition that AB bigger than Y actually becomes CD lesser or equal to Y. And once you have the CD lesser or equal to, and the summation m power and k is small, lesser y by 2, and therefore m power minus alpha and m minus k, this m minus k power minus beta will play more or less the same role as m power minus beta, and therefore your m power minus alpha minus beta will come out. And then you have the summation over C dividing m, D dividing m minus k, C power alpha, D power beta, with CD lesser or equal to 1. And yeah, that's exactly what you are getting. CD lesser or equal to y, the C power alpha, D power beta, and the summation over m not exceeding y, m congruent to 0 modulo z, and m congruent to k modulo d, m power minus alpha, m minus k power minus beta. And this m power minus alpha, m minus k power minus beta would essentially give you a y power alpha minus beta divided by the GCD of C and T. Because as I told you, m power minus k is something very similar to m power minus m minus k power minus beta is something very similar to m power minus beta. And therefore, the what you have the inside sum is something like an m power minus alpha minus beta. And that summation m power minus alpha minus beta, when you sum over up to y, subject to these congruence conditions, m congruent to 0 modulo c and m congruent to k modulo d, would give you something like a y power 1 minus alpha minus beta divided by the GCD, divided by the LCM of CD. And then you have the C power alpha, D power beta. Which now the conditions on CD is that CD is lesser or equal to y. And that is precisely what we had done earlier. CD lesser or equal to y, C power alpha, D power beta. CD is lesser y power beta, and that's exactly what we get. Now we go back, and now instead of again CD lesser or equal to y, I can now I can actually replace it by the LCM bigger than or equal to x. And the way again to do that is, of course, to split the sum in terms of the GCD, and then this equation 6, whatever you do, will look like the equation 5, and then you can use this equation. And now I want to say how this, by a simple convolution method, gives you the estimated estimates. Therefore, we recall capital F equal to 1 star F and capital G equal to 1 star G, and we are interested in the summation A dividing N, B dividing N minus H, F of A, G of D, with H lesser or equal to N lesser or equal to X. And here now I break the sum into 2 parts. The one part is AB lesser or the LCM lesser or equal to X. The fact that I am breaking it as an LCM lesser or equal to X is rather very important. You know, if I don't do that, if I just take AB lesser or equal to X, then I seem to lose the uniformity in H. Therefore, if I want to really keep the uniformity in H, then I need AB lesser, LCM AB is lesser or equal to X. And the S2 corresponds to AB bigger or equal to X. And now the thing is, as far as the S2 is concerned, you have a summation N not exceeding X, A dividing N, B dividing N minus H, and with the extra condition that that should have been in LCM in S2 also. In S2, with the LCM bigger than or equal to x, and that is precisely what we handled in 6. And that we have proved is the error, is the O of the error term of the type which we expect. And now you have to bother about the S1, and the obvious way is in S1 to interchange the summations. And when you interchange summation, you have a summation over A, summation over B, f of A, g of B, n congruent to 0 modulo A, n congruent to h modulo B. And therefore, this is summation AB dot exceeding x, f of A, g of B, x minus h by AB as to be expected, plus order of 1. Now look at this error term, summation f of A, g of B with AB less than or equal to x, and this sum is LCM AB less than or equal to x. This sum is precisely what we have done in the equation 3. 1 over A power alpha, B power beta, when you sum over A and B with the LCM less than or equal to x is O of the expected error term, and therefore that can be taken care of. And now you take this AB sum and extend it up to infinity. And you extend up to infinity, then you have an f of A g of B divided by the LCM of AB with the LCM of AB bigger than or equal to x. But the LCM of AB bigger than or equal to x, f of A g of B is already you have done, and not with the f of A g of B. But in order to make our life simpler, I have already assumed that f of A is O of A power minus alpha and g of B is O of g power minus beta. And therefore, instead of estimating f of A g of B, I can as well estimate A power minus alpha, B power minus beta. And that estimate A power minus alpha, B power minus beta, where the summation is over all those ABs which are lesser than equal to x. And that is already done with the equation 2. 1 over A power alpha, B power alpha, LCM of AB bigger than or equal to x is O of Ax by x. And that's exactly what we did. When you do this actually gives you an asymptotic formula for sigma n plus 1 by n plus 1 n by phi n and sigma n plus 1 by phi n, which is because you can take sigma n plus 1 by n plus 1 into n over phi n, but this n over n plus 1 will not play a major role at all. And therefore, you can actually estimate sigma n plus 1 divided by phi n. Therefore, this is also a product of, in some sense, of the form. Okay, this is not exactly of the form G1n, G2n minus h, but on the other hand, with the extra factor n over n plus 1, this can be the sigma n plus 1 divided by phi n can always be written of the form G1n, G2n minus h, and this n over n plus 1 is not going to make a role. And then this gives you an error term which is much better because you get an error term which is O of x power epsilon. And that is essentially because, you can choose your alpha to be more or less 1 minus epsilon. Therefore, let us know what's my alpha. My alpha is the little o f is such that f of n equal to O of n power minus alpha. And therefore, if the capital F is phi n by n, then for the capital F which is phi n by n, then when you compute what is the little f, then that is actually O of n power minus 1 minus x. But on the other hand, this is L infinity of the little f. And that's exactly what I was trying to say. But on the other hand, my earlier result was actually the L1 of little f. And since it was on the L1 of little f, that result is definitely better. But on the other hand, and I don't even need the multiplicativity. I don't need anything at all. This can be proved. But on the other hand, it's not clear to me at all how one would be able to get a uniform estimate in this particular case. And now I want to say that this method, this simple convolution method of the shifted sum, can be used not only to sum the summation n not exceeding x, but even the summation p not exceeding x, you can use it. For example, summation p not exceeding x, phi of p plus 2 by p plus 2 into phi of p plus 1 by p plus 1, for example, that will be the Li of x. into the constant that LI, because again, when you are looking at the functions f and g such that f and g are close to f of p and g of p are close to 1, and then when you sum over p not exceeding x or such function, then what you would expect is a constant times Li of x. And therefore, this will give you a Li of x, and the constant is what you are interested in. And the constant is p bigger than or equal to 2, 1 minus 1 over 2 by p into p minus 1 plus order of x over log x power a minus 1 for any a positive. And I was a little surprised when we had this result, because in the literature already that the results were only essentially x over log x power 1 plus epsilon. And you don't, I mean, you can actually save any power of log x. Okay, in order to see why you can save any power of log x, you use the same method. You write the s, which is the summation over p, and a dividing p plus 2, b dividing p plus 1, and the p you are writing, which is mu of a by mu to mu of b divided by ab. And then you can interchange the summation. And first of all, again, you break it as the LCM of AB bigger than or equal to x. But in this particular case, the LCM is the same as the product itself. I mean, because I am looking at the special case when A divides P plus 2 and B divides P plus 1, and P plus 1 and P plus 2 are co-prime, and consequently A and B will be co-prime. And therefore, the LCM of AB is the same as the product AB. And in fact, here, of course, since the estimate is going to be rather very small, therefore I am not even going to sum over primes, I am going to sum over all integers. Therefore, I have a dividing n plus 2, b dividing n plus 1, 1 over ab. And that part, which we have already seen, is O of log square x. And the part corresponding to the LCM of AB bigger than log x power a, and that part, you just write summation n not exceeding x, a dividing n by 2, b dividing n plus 1. The LCM of AB being log x power a and lesser or equal to x, 1 over AB, which is summation 1 over AB. And then the interchange the summation, you get x over AB plus O of 1. And this part is also small, essentially because you are assuming that the LCM of AB, which is equal to the product AB, is bigger than log x power a. Since the product AB is bigger than log x power a, you can save any power of log x. Now the part AB less than or equal to log x power a, and this part is easy because then you can interchange the summation, and then you end up with the n congruent to minus 1 modulo, minus 2 modulo a, and the n congruent to minus 1 modulo b, which means that n congruent to a certain number modulo ab. And now this ab, which I am now assuming to be less than a power of log x, and once you have assumed that AB is less than a power of log x, then the theorem on primes in arithmetic progression would give you an asymptotic formula. And I use that asymptotic expansion, and then you will get, of course, a midterm, which is small n. Therefore, this way you can actually save any power of log x in this. Now, the same method gives, assuming that fjn is O of n power minus alpha, which, of course, let me again recall, this is much stronger than the assumptions which earlier people have made, namely because the first method which I was discussing, I needed only that little f1 p plus little f2 p plus little f3 p, etc. divided by p is convergent. But here I am now assuming much more that fj of n is O of n power minus alpha. And once you do that, then one can even get an asymptotic formula for f1 of any polynomial. And in fact, okay, let me be slightly careful. I can get f1 of any polynomial except for the fact that I mean, it's not, doesn't seem to be even easy to write the main term. I mean, the method should work type. But on the other hand, if it is a linear polynomial, you can do that. And similarly for quadratic polynomials, n square, the little f2 should be capital F2. The capital F1 of n square a1 plus n square a2 plus fk of n square ak, that you can get an error of x power 1 minus alpha plus epsilon. And actually, given some random a1, a2, etc., ak, I don't even know how to write the main term, because the main term can be written in in terms of the congruence conditions on many things. For a given A1, A2, I can write it. For a generic A1, A2, it is not very clear to me how one would be able to write an expansion. But in some special cases, if you want, then it is really possible to write an expansion. Okay, for example, this is the one. Suppose you take your function to be phi alpha by n power alpha. Therefore, this is a function which is phi alpha by n power alpha, then which is evaluated at n square plus 1. Therefore, n square plus 2 and n square plus 3. And that is where it is evaluated. And therefore, I am taking A1 equal to 1 and A2 equal to 2 and A3 equal to 1. A3 equal to 3, and that's all, only 3 terms. And then if you do that, then it is possible for me to write actually what is the main term. And this main term is a constant, which I won't bother, times the product P bigger than 2, 1 minus 3 plus minus 1 over P plus minus 2 over P plus minus 3 over P by P power alpha plus 1. And the error term is O of x power 1 minus alpha plus 1, as I was telling you all the time. Okay, now what is the value of 3 plus minus 1 by P plus minus 2 by P plus minus 3 by P? And that depends upon what are the congruence conditions for P modulo 24, as you would be expecting. And then depending upon the value of P modulo 24, then you can explicitly write what these 3 plus minus 1 over P plus minus 2 over P plus minus 3 over P are, and then you can simplify. And now, I think this method can also be used for the shifted sum with mu square n. And this is something where I will be like to spend some time. And let capital G equal to G star 1, and assume that little g of n is over n power minus n, this little g missing. Then uniformly with h, summation mu square n g of n minus h is O of x minus h into k of h plus, now I get O of x power epsilon e of x by a, where e x a is x power 1 minus alpha when alpha is lesser or equal to half, and x power half when alpha is bigger than half. And this k of h is ab bigger than or equal to 1, ab dividing h, mu of a gb by a square. And as I was telling earlier, these results do work even for h is equal to 0. And if h were equal to 0, then this GCD condition, that GCD of AB divides h, of course, will disappear. Now, one of the things which one can ask is that if alpha is bigger than half, is this, and suppose you get something like an x power 1 minus alpha for every alpha, then, okay, that is probably what you would say that you would expect, that it is O of x power 1 minus alpha for every alpha. But on the other hand, I am not getting it. I am getting for alpha bigger than half, I am getting x power half. And therefore, for example, even if alpha equal to 3/4, where I would expect x power 1/4, I am only getting x power half. And okay, therefore one would ask whether it is probably the inherent weakness in the method, or probably is there some reason why one would get only x power half and not anything better. In order to do that, let's take h equal to 0. And when h is equal to 0, and you take away your g of n equal to phi n by n, because we have always been arguing for g of n equal to phi n by n. If g of n equal to phi n by n, then the summation which we are looking at is mu square n g of n divided by, mu square n phi n divided by n. But if you are looking at this mu square n divided by phi n divided by n, and now if you are looking at the generating function of that, then the generating function is zeta s divided by zeta 2s times a nice function. Now the generating function is zeta s by zeta 2s power nice function. And once you are given that, and when you are looking at n not exceeding x of a function like zeta s times zeta divided by zeta 2s times a nice function, then you see that you cannot improve the result better than O of x power half. Maybe you may be able to gain something like an exponential minus c root log x or something like that. But obviously, gaining of an amount of x power minus epsilon is completely ruled out. Because if you gain an x power minus epsilon, that would essentially say that the denominator zeta 2s has no zero in sigma bigger than half minus epsilon, which is the same as saying that the zeta function has a good zero predicate. And therefore, that is not really possible. And therefore, this x power half cannot be improved. But on the other hand, as I said earlier, whether this x power half cannot be improved probably by e power minus c root log x or some such small function, that is not very clear. Because since we are not using any analytic method, we are essentially using the convolution method. And in the convolution method, it is not very clear to me that for just a general function capital G, summation mu square and capital G and minus h, how would be able to prove, if at all it is true, that the summation is O of x power half e power minus c root log x. And the main term, of course, k of h is summation ab bigger than or equal to 1, ab dividing h, mu of a, g of b by a square b. Okay, now let's look at the proof. And I should also point out where I am getting this x power epsilon. Okay, whether this x power epsilon can be avoided. Okay. As before, we break the sum. We have the summation n not exceeding x, mu square n, g of n minus h. And then your summation over n, summation a dividing n, b dividing n minus h, mu of a, g of. Yeah. It should be a square dividing n. U square, okay. Now T1 corresponds to, now we break the sum. This is yes, sorry, the one is not a dividing n, a square dividing n. And the T1 corresponds to the LCM of a square and b lesser or equal to x, and T2 corresponds to the rest. We first consider T2. As before, we split the sum depending upon the GCD of a square b, and therefore that reduces to estimate summation over n, ca square dividing n, b dividing n minus h, something like an a square b bigger or equal to z, b power minus alpha. And this summation is something which I have not been able to estimate it without losing the epsilon. And I would like to even tell you where I am sort of losing the epsilon. Okay. Now we make the dyadic division with A in A, B in B, and then we look at the summation L, and we take that dyadic part L of A comma B. When you take the dyadic part L of A comma B, then you are summing over n not exceeding y, ca square dividing n, with the ca square dividing n with a around a, and cb square and b dividing n minus h with b around b, and which is a extra condition that a square b bigger than or equal to z. But the condition that a square b bigger than or equal to z would of course translate on the capital A and capital B, and therefore you will get a capital A square times capital B is bigger than or equal to z, and therefore that won't play a role at all. That we can take out. Now I have a double sum. Now I want to know whether I can take this double sum and interchange and to do something with that. And that is not very clear to me how to do that at all. And if I have a summation over n, and then you have a summation over a with the condition that ca square divides n, and the summation over b with the condition b divides n minus h, and then interchanging, I don't know how to do that. Therefore, the only thing which we do is then the summation over b power minus alpha part, I sort of take it out the L infinity now. Therefore, I have the summation over b power minus alpha. I take out the L infinity now. And therefore, this b power minus alpha gives you a capital V power minus alpha. And then there's this condition which says that b divides n minus h. And that gives you a divisor function of n minus h. And once you have a divisor function of n minus h, and therefore that gives you an epsilon. And that is exactly where I lose the epsilon. And in fact, if alpha were, okay, therefore, how do you really sum over b dividing n minus h b power minus alpha? And if you take the L infinity now, how can you save an epsilon? It's not very clear. And that, in some sense, needs probably the summation of the divisor functions in a very short intervals and so on, which I don't know how to do. And therefore, when you do the summation, then this LAB becomes y power 1 plus epsilon divided by C AB power alpha. And sorry, that should be little c. Therefore, little c won't play a role. You have an AB power alpha, but on the other hand, you see the conditions. Yeah, the condition that A square B is bigger than or equal to Z would mean that capital A square times B would be bigger than or equal to Z. And once you have summation over 1 over AB power alpha, sum it over capital A square B bigger than or equal to Z, and then when you do the summation, then that L actually becomes O of y power epsilon by C y over Z power alpha E of y. And now once you do that, then the rest of the proof is straightforward. Now you have this, the T2 summation has been estimated as y power epsilon by C y over Z power alpha E of y. And now you have to look at the T1 summation. And as far as the T1 summation is concerned, we know how to do it. I mean, okay, as I told you, it was A square dividing n, and therefore you utilize the summation. You have a summation over A and B, and then you have a mu A times GV, and then summation n congruent to 0 modulo A square, n congruent to H modulo B. And now you take this n congruent to 0 modulo A square, n congruent to H modulo B, and not exceeding x, and that will give you x over the LCM of A square B as usual, and that the summation mu A GB you have to sum up, and that should give you the weight term of what is expected. That should give you, that's exactly the weight term which I have really written, namely AB bigger than or equal to 1, AB dividing H, mu of A GB divided by A square. And I think more or less I would stop there, and would be happy to answer any questions.
Yeah, let us thank Professor Balasubramanian for this wonderful talk of explaining these analytic intricacies of analytic number theory. And now, if there is any questions. There are any questions from the audience here, and then we'll move into this YouTube channel if there are any. Yes, so it seems like there's no question here. And is there any YouTube?
There are no questions, sir.
No questions? Okay, so actually it's, and Professor Balasubramanian is so quick into his thinking about all these arguments that, you know, sometimes I really get amazed the way when he explains that his thought process really moves so fast. So it's a wonderful talk, sir. And thank you so much for your time for us. And we'll soon see you here.
Oh, sure, definitely.